Okay, let's show that a compact subset of a Hausdorff space is closed. So I've prepared in advance an illustration here of what's happening. So we have some topological space X, namely, in this case, a Hausdorff space, and some arbitrary subset denoted C here, and it's compact because it's a condition in this proof. And we want to show that the compact, this compact subset C of X is closed. And so what I've drawn here will prepare us for some of the details in the proof to come. So points here, Y and Z, are just two arbitrary points in the subset, and the point X is just a point in its complement within the space X. So the red circles indicate open neighborhoods around, or correspondingly, they represent open neighborhoods around their points, and similarly for X and Z, the pair X and Z, I've drawn two neighborhoods that are disjoint, and I've given them names. So let's go ahead with the proof. So let's define a point in the complement. So let X be an element of the complement, and we let Y and Z be points within the subset C. Now we know that X is a Hausdorff space. So what does that mean? If we take two arbitrary points in the space, we can find disjoint open neighborhoods around each of the points, each of those 2 points. So let's write this down. So X is Hausdorff. Hausdorff space, meaning X and Y have disjoint open neighborhoods. So let's clarify what this means with some notation. So if we have Vy, here, this red circle here, and it's a given open neighborhood of Y, then there exists a corresponding open neighborhood of a point in the complement, where if you draw an open neighborhood around that point in the complement, it's necessarily disjoint from the open neighborhood around the point Y. And this is because the space is Hausdorff. So let's write that down. Vy given open neighborhood of Y and Uy. So this notation, the U and V, will be a lot clearer later on. Uy, the corresponding. So as I was going through this proof, this is where a lot of my confusion came about, was the correspondence between the open neighborhoods. So that's why I want to make it explicit here. Of X. So this is why we have this Y subscript. It refers to this correspondence. So the Y subscript reflects this correspondence. Okay. So we can do the same thing. So what I've drawn here is an iteration of what I've just done, just to make the point clearer that we can do this for any two pairs of points, where one of those points is in the subset C, one of those points is in the complement, and we could repeat that. And that's why I've done it for the point Z here and its respective disjoint open neighborhood in the complement UZ. So I'll just write that down without writing it all out again. So where do I write this? So consider Z in the subset. Similarly, X and Z have disjoint, so I'll just write dots. So this is what I would write. So I'm not going to waste time on that. And yeah, the same thing happens here with this statement. Okay, and I'll write that we will iterate this process. So we iterate this process for all points C in the space, in the subset C. So for all points in the subset, there exists open neighborhoods let's call it VC, the open neighborhood around the point C. And obviously, C lives inside this open neighborhood, and its corresponding disjoint neighborhood, UC. And by definition, we have that X lives in here, such that the intersection between these two neighborhoods is the empty set. Okay. And this what I'm about to write might seem a bit repetitive, I just want to clarify a point. So let's define VC to be an open neighborhood of a given point in the subspace and UC to be the corresponding open neighborhood of the disjoint of the point in the complement, the corresponding point. So I'll just make it very clear. This is allowed since X is Hausdorff, so it's a Hausdorff topological space. Very good. Okay, now let's proceed. Now we know that we have an open cover of C. So let's form this cover. by taking the collection of sets of open neighborhoods around each point in the subset VC, such that C is in the subset. So that collection forms an open cover, and remember each of those sets here is open. So open cover of or for C, and since, as I said, each of these is open, for all C and C, and C is in each point, each of these neighborhoods by definition. Very good. Now we want to use the compactness of C somehow. And this is, I guess, necessary and crucial for this proof to work. So let's see how. So since C is compact, so what is the definition of compact? Every open cover of that set admits a finite subcover. And obviously this is just a topological definition of compactness, but this is what we'll use here. So since C is compact, every open cover of C admits a finite subcover. And the finiteness is crucial here. So what does this imply? So there exists some collection of points C1, C2 to some Cn in our subset such that subset is contained in the union of each of these open sets or open neighborhoods. All up to VCN. This is our cover here, and it's finite. Okay, what do we do now? Now we want to consider the using the Hausdorff condition. We have those corresponding open neighborhoods in the complement. So now consider the corresponding open neighborhoods of X and these are namely UC1, and we're using these subscripts C1, C2 to make it clear that we're corresponding with those open neighborhoods here. So UC1, UC2, all the way up to UCN. And we want to let we want to define a new set, U, to be the union of all of these open neighborhoods. So U, C, wait, did I say union? I meant the intersection of these finite sets here. U, C1, intersect U, C2. U, Cn. So you can imagine what's happening. We're taking points in our space C, and we're kind of, I guess, making pairs between the point in our set C with the point in the complement, drawing open neighborhoods around them, making sure that they're disjoint, and taking a finite intersection of these open neighborhoods. So we've just defined this set U. So note that we have that U, well, since U is an intersection of finitely many open sets. So we have a finite amount of open sets here we're taking the intersection of. Then U must also be open. Well, obviously this requires a separate proof, but it's we're just going to make it as a we'll just make this claim now and claim that it's true. So it requires a separate proof. Now we want to show that when we take the intersection of our set here, U, with our subset C, that we have the empty set. So we now show that U intersect C is the empty set. And let's kind of do this, I guess, by some contradiction. So let's suppose we have some point in this intersection here, point C dash or C bar, living in this intersection. So since C, well, we have a cover for C. VC, make it a V, C2, all the way up to VCN. We know that for some I in this index, well, there exists an I in this set, such that C dash lives in one of those open neighborhoods. Okay, but we know that U, well, it's contained in U Ci for some I, and our point here, C bar, lives inside U because we've made this supposition here. And by set inclusion, we have that our point C bar must be in UCI using this and this. Well, is this possible? No. So this cannot be possible. Well, we know that each, as we've defined, U, an open neighborhood U and another open neighborhood V, as we've defined it, they're disjoint, since X is Hausdorff. So this cannot be possible since UCI and VCI are disjoint. And that's since X is Hausdorff. Well, that's our contradiction. So that implies that the point we've supposed existed does not. So if no point exists, then we have that the intersection, this one here, must be empty. Very good. So what does that mean? We have that, well, U, well, it's an open neighborhood. Which we've shown of X, and it's disjoint from C. So remember how we've defined U to be the finite intersection of all those corresponding open neighborhoods. So U is an open neighborhood of X, disjoint from C, from the subset. Well, we've chosen X here. It looks like we've picked a precise location just for the purposes of the sketch, but the point X here was just some arbitrary point in the complement. So this works so long as that point X is chosen to be in the complement of our subset C, but still within X. So since X in the complement was arbitrary, so now I'll say this, arbitrarily chosen. Well, we can repeat this process for all points in the complement. This process can be repeated for all X in the complement. Oh, I need more space. I was hoping to finish at that point. I might shift this. Okay. What do we have now? So hence, for all points X, we have an open neighborhood. There exists an open neighborhood of X. And what's special about this is that it is contained in the complement. So you could kind of sense why we've done all of this. Because remember, we just want to show that it's easy to forget we're trying to prove, but we want to show that this set C is closed, and the definition of closed, or a consequence of being closed, is that its complement is open in the set, in the topology. So there exists an open neighborhood of X contained in the complement, which means that the complement is open, because we can draw neighborhoods around any point in the complement and still remain in the complement. So the complement is open, implying that a subset is closed.